by a charge at the origin, by a charge Q at the origin is E equal to 1 4 pi epsilon naught. Okay, which can be written as a gradient phi, as a gradient, where phi r is equal to
是不是少一个 Q 啊？
1 over r,
是不是少一个
right?
Q？
Okay, gradient r. Okay.
Teacher.
R is partial x, partial y, partial z, 1 over r.
Teacher,
Yes.
is there a Q at electron field?
By charge Q at the origin.
The electric field.
Q field. Electron field.
Electric field has a Q there.
Electric field.
Electron field. Q.
What?
You left the Q.
Equation.
Equation doesn't have Q.
Oh, sorry. Sorry. Okay. The gradient of 1 over r is that one, and it can be derived. Okay. We know the partial x r is equal to 1 over x, right? So that can be first derivative minus r squared, and then r, I take a gradient, so that's rx, ry, rz. Okay, so that is equal to minus r, right? Okay, so in general, okay, principle of superposition for charge distribution, phi r equal to 1 over 4 pi epsilon naught. Okay. R minus R prime. Rho R prime. Integration of that. Okay. Now. Okay. So we know that divergent E equal to Gauss theorem of which is Groups law, right? Means that when you insert that into that one, this means Laplace phi equal to minus, so that the electric potential satisfy a Poisson equation, okay? So the electric field satisfies the Poisson equation. We can. Okay, I want to rederive that from the point of view. Okay, first, let's take a look. Laplace. Okay, let's take a look at this one. Laplace of 1 over r. This is very important. And so Laplace divergent gradient. As I just say that, so this is divergent okay. And that can be easily calculated. Divergent means partial x plus partial y plus R plus partial Z. Okay, and this can be easily calculated. X, okay. When you calculate that, you first differentiate the first term, and that equal to 1 plus, okay, x, you make it a differentiation of R3 to the R. So that's minus 3 R to the 4th, and then R, partial differentiation of R with respect to x. That's 1 over x. So this is minus R to the 5th 3y squared plus minus R 3z squared. So when you add up, it is 0. It is 0 for R equal to 0. Okay. So we can equal to 0 for R not equal to 0. Okay. Anything. Okay. Same thing. Okay. And so let's apply Laplace into the phi R. Okay. So okay. So Laplace phi is equal to what? 1 over 4 pi epsilon naught. Okay, and only this one is a function of R, so rho R doesn't matter. Okay. Rho R prime Laplace R equal to R prime. Okay. Okay. Now, first of all, okay, when R is not equal to R prime, this is 0. This is 0. Okay. But before we do that, let's take a look at this one. Gradient. Okay. This involves differentiation with respect to R. What happens if I want to do that differentiation with respect to R prime? This can be easily equal to gradient R prime. Right? So the same thing is divergence. And make it divergent Laplace is divergent gradient. Okay, and first of all, you make that one, and the same thing. This one is R minus R prime. So we do the same thing. This is equal to minus the prime dot minus gradient. So the point is, Laplace, when you do this is the same thing as when you make it in R minus R prime. Okay? That's a simple fact, because R and R prime are, we have the opposite sign, and that's it. It's symmetric. Opposite sign. You get 1, you get a minus sign, you get twice Laplace, you get the same sign. Okay. So we can convert this, into rho R prime Laplace. Okay.
老
the
师，
same thing.
老师，
Yes.
可以再说一次为什么那个就是变成 from 之后就变成 yes yes 就是
Okay, when you make a plum, you just change it out. You get it. What happens if that one? You get this.
倒出来。
You get the next side, right? The same things involve also divergence. Okay? Because R and R prime, it always appear in symmetric but opposite side, right? Intersymmetric. With respect to the interchange of R and R prime. Okay? Does that answer your question? Okay. Now, as we said, when R is not zero, this is zero. Okay? When R is not zero, okay, this integration, okay, when R is here. Okay? When R is not equal to R prime, okay, you are doing integration of R prime. Everywhere is zero except here surrounding the R, right? Okay? So we can reduce this integral volume integration. Everything is zero. Right? So this integration can be reduced to a small sphere, okay? To this small sphere. This small sphere, what do you call it? We call it sphere, right? Sphere. Okay. Same thing. Rho R prime. Okay, and Laplace. Okay. That's not I'm done. But when the radius of this sphere is very tends to zero, okay, when the radius of that one, because the charge distribution is continuous function, so you can when the sphere D, okay, when the radius of the sphere tends to zero, rho is always the same thing, so you can take that out as rho R plus for continuity, because it's continuity. As your radius goes to zero, the difference goes to zero, right? So you can take that out. Rho R. Okay. Laplace prime. Right? Okay? Very simple. Okay? Now, what is Laplace? Laplace is gradient divergence. A divergence gradient. Okay. So it's a divergent, so you can write this as a divergence, okay, from a gradient, right? Okay, now you can use the Gauss divergence theory. An integration of a divergence is equal to the surface. It's equal to the surface integral of the upper surface integral of. So this is equal to rho R 4 pi epsilon naught. Okay. Okay, R on the surface. And dot gradient. Square A, okay, this surface area integration, right? And that can be calculated. That is nothing but okay. What is this? This is actually R square R. Okay. Right? So this is the radius, the area of that is 4 pi times the a squared, where a is the radius, and this is a radius. And then that is the r, okay, the integration, which is actually minus n. Okay? N dot n is equal to 1, unit vectors. So you have a squared cancel out. So this is minus rho r epsilon naught. Okay, so we prove that. Okay, something. Okay, so we prove that. Okay, after such a long. Okay, prove that. When you have a phi equal to that, so Laplace phi equal to, okay, minus epsilon rho. And what does it mean? Means that means rho r prime Laplace right. So this thing, you know, when r is equal to r prime is 0, and the integration is 1, 4 pi. Okay, 4 pi. So this actually means so that is equal to rho r times minus 4 pi, and you can just make it a shorthand that, you know, the plus is equal to minus 4 pi delta r minus r plus, where delta is a Dirac integral, three-dimensional Dirac function, where this one delta r equal to r prime equal to 0 for r not equal to r prime, and then delta r minus r prime equal to 1. That's the Dirac delta function. Okay? And because of that, you have any function, okay, delta r minus r prime, when r not equal to r prime is 0, so you can take that out as a rho r. Okay, that is the definition of Dirac, three-dimensional Dirac function. Okay, so you can just simplify, forget about everything, just memorize this formula. Okay, then you become the expert. Just memorize this formula, okay? Expert want to go through all this derivation. Okay, what I have done is just show that, okay? Show this relation, and this relation is very useful. We will be using this formula again and again and again, okay? And this is a delta function, okay? Okay. And that's okay. That's the minus sign because you should be careful, how the sign. So this is delta function, okay? Sometimes we call it green function, the 4 pi factor, something like that. But anyway, it's all the same, okay? So memorize this, and then you can save a lot of energy. Okay, whenever you have that one, okay, you just remember this is the minus 4 pi, three-dimensional delta function. Okay, three-dimensional. Remember, three-dimensional delta function is not equal to one-dimensional delta function. That you should be very careful. Okay, you have 4 pi and you have r squared volume integral. Okay. So, any question? Okay. So, so we have that. Okay. Now, okay. So I can erase this. Okay. So. Okay. Now that's again. Okay. So we have a divergence equal to E. Okay, and then as E as a gradient implies plus 5 equal to minus epsilon rho. Okay, then this Poisson equation. Okay, and the solution of that Poisson equation is equal to 1/4 pi epsilon naught rho of okay. So that's what we have done that, but I just want you to remember this one. Just be using that again and again. Okay. Okay, so that's the electric field. Okay. Now for the magnetic field. Okay. As I show you, the Faraday's law of induction. Faraday's law of induction say that. Okay. Okay. For this is static. So for this, okay, when you have a gradient, again, that means it could be R1, 2 is equal to 5R2 negative minus 5R1. Okay. For static Coulomb field. Okay. For static, you can have that one. And the simple thing is, from this, a circle integral, a line integration around a contour is 0 for static electric field. Okay. However, Faraday's law of induction, the importance of that. First of all, in the changing field, okay, magnetic field, okay, this is non-zero, and this quantity, which is called EMF, electromotive force, is not zero, and that is equal to the total negative of the total change rate of the magnetic flux. Okay, and what is magnetic flux? Magnetic flux is the surface of B dot N. Okay, it's the surface integration of the magnetic flux. That's why you call it magnetic flux. Okay. Okay. And by this one, this only on this surface, so one surface, second surface. Okay. This implies the validity of Faraday's law of induction implies that. Okay. The same surface, this surface 1, surface 2, okay? The magnetic flux should be the same. Okay, rate, just the rate, not some constant. Constant, we don't care, okay? So it means that the magnetic flux of the total magnetic flux doesn't depend on that. That means you can change it out. That means the total magnetic flux in in and out. It's always the same. It's always 0. Okay. That is in contradiction. That is a negative version of Gauss divergence theorem, right? Gauss law means that the total outgoing flux, net flux, is equal to the total charge involved. And there's no magnetic charge, so that's 0. And that 0 implies, okay, divergent B. 0, right? Because this is equal to divergent B by Gauss divergence theorem. Okay. I emphasize again and again and again. We will be using Gauss divergence theorem again and again and again. Okay. In addition to the Stokes theorem. Okay. So this is a magnetic version of of magnetic version of Gauss law for the electric compared with the electric field. Okay. Now, in a static field, ampere circular law means how much is that? Ampere circular law. We have a okay. The line integral of the magnetic field around the curve is equal to mu0 times the total charge going through. Okay. So this is okay. J dot n. This is Stokes theorem. No. This by definition. Okay. And by Stokes theorem, this is equal to B dot curve B. Sorry, curve B dot n. The normal component of the curve B. The surface integral of the normal component of the curve B. Okay, so the differential form. So the differential. Okay. This one we use this one. Okay. Orange. Okay. So, by using Stokes theorem, this one is equal to that one, and that one is equal to that. So the differential form of Ampere's law is curl B equal to mu naught J. Okay, that's Ampere's circular law. Okay. It's called Poincare lemma or Helmholtz theorem. Okay. When you have that one equal to 0, that means B is equal to curl A. Okay, Helmholtz law. And curl E, when you have the curl E equal to 0, that means E is equal to gradient phi. Okay, and I think this is called Poincare lemma. Okay, and that can be proved by Helmholtz theorem. Okay, I think this is Helmholtz theorem. Which you should take a look at the appendix. I think I gave you the appendix, which give you a proof, okay? now, but okay. Anyway, you should use it. That's very important. Okay. So, by using okay, it is 1.1. Okay, divergence B is 0. So B is a curve of a vector, which is this vector is called vector potential. Okay, later we modify this will be modified by Maxwell's displacement current. Okay, so we'll talk about it again. Okay, now so we have that, and this is vector potential. Okay, as I told you, you have a scalar potential, you have a vector potential. This is actually in relativistic. This is T and R covariant. And in fact, Maxwell equation, can be derived by requiring the Lorentz covariance of the space-time. Okay, and that's why you have a phi, you have a scalar potential, you have a vector potential. Okay. That's why you have a magnetic field, you have an electric field. Okay. Now, if you insert this into the Ampere circuit law, okay, then you have a curve equal to mu naught J, right? And that is equal to gradient divergent A minus Laplace A, right? Okay. And so under the condition divergent A is 0. Okay. Okay. Later, let's see. There is a lot of selection of A. And you have a gauge invariance or whatever. Okay, matter what. If this one is 0, okay, this is called transverse gauge. Okay, this transverse gauge is very important in QED. When you want to talk about quantum chemical interaction between light, between photons and matter, always use this one, Lorentz gauge. And 5 turned out to be just Coulomb field. Okay, so that's Coulomb field is static, and this is related with the okay. In every case, let us assume divergent A is 0. Then we have this one. Okay, under the condition divergent A is 0, then this implies Ampere's law implies Laplacian A is equal to J, right? Okay. So okay, by the way, I should warn you, okay. When you write that 1 equal to that and that, okay, if you are not using Cartesian coordinate, you should be very careful. Sometimes this will, you can easily go to mistake, some additional term coming out unexpected, you don't know why, okay. But in Cartesian coordinate, there's no problem, okay. In curvilinear coordinate, you should be careful. This is not completely right, Okay. Any case, try to use when you make this expansion, you have two curves. You better make it in the Cartesian coordinates. I think in curvilinear coordinate, this maybe okay. I forgot the example. Okay, anyway, for condition. But in any case, each component of A, AX, JX, AY, JY satisfy this Poisson equation, right? Satisfy the same Poisson equation. What's Poisson equation? Yes. Right? So, we have a solution. It's component. So we have a solution. Okay, AR equal to R minus R prime. Okay. J R prime. Okay. Vector potential. Okay. It's given like that. Actually, this is what you call it. This is completely equivalent to what? To the Biot-Savart. Okay, as you will see. This is completely equivalent to Biot-Savart. Okay. Okay. And you can easily show that divergence A is 0. Divergence J, the current is concerned. So that's no problem. Okay. So that's the solution. Okay. And this is actually Biot-Savart law. Okay. Because for that, okay, AR, then your B, this is actually Biot-Savart law. Because you write it down. This is actually B. BR. Okay, I did it. Bring my note. I always it's panic when I go up in front. Okay. BR is equal to curl A. And that 1/4 pi mu naught, right? Curl again. Curl only these factors. 1/r minus r prime involved with r. So when you do the curl, okay, curl is curl times. So you change the because the gradient is derivative of that. So you have to change that. So the vector. So this is minus coming from J R prime. Okay, so because you are interchanging the order of vector product. Okay, originally this is curl. Originally this is this one, but this one as that one, you know. And of course you can down that one, but when you have a gradient, you want to change order, you know, that's more convenient. Okay, and then you can do that. So that one is equal to 4 pi mu naught. Gradient R. So the gradient R equal to minus, right? So the minus sign is the minus sign here. This minus sign because you are changing of the vector, and then again you have a minus sign of there. So this one will give you R minus R prime to the cubic. Okay. So JR prime times R minus R prime. Okay. And this is actually Biot-Savart's law. Okay. This actually is Biot-Savart law. So you have a current. Okay, when you have current J E3R prime or whatever, and it becoming DL, right? That means J of the horizontal is I, so that equals to R J dr. Okay, the dr. Okay, give you the directions. The length, okay. dr is this one. Okay, so and R is R prime, and then R is R prime, right? So R equal to minus R prime, right? Okay, the distance between the viewpoint and the source. So this, if you current is 4 pi mu 0 I. Okay, dr J, that's dr times R 3 to the R. Okay, right? That's simple. Okay, and that's Biot-Savart law. Okay, and you can write it. Vector potential is 4 pi mu 0 R, right? Okay, R dr prime. Okay. Okay. Current. Biot-Savart law. Okay. So, again here, it depends on. Okay. Here, of course, you always can use it, but here, when you write it down, okay, this is only true when J is conserved. Okay. So, any question? Yeah.
You said that the magnetic fluxes for surface 1 and surface 2 were the same, right? So in which cases the magnetic fluxes are not the same?
What?
You said that the magnetic fluxes for the surface 1 and surface 2 were the same, right?
Yes.
So in which cases that the magnetic fluxes are not the same?
No, they are always the same. Okay, you have that one, right? You have a circle, right? You have suffix.
So they are always the same.
And then you have that one, the suffix, right? Okay, but they are all have the same this boundary condition. And the change, when you talking about the change of magnetic flux, total magnetic flux, right? You means the total magnetic flux going through a surface surrounded by this closed curve, right? And this surface can be that one, right? They should be the same, right?
Yeah.
And that means, so, okay, this is an argument, In a way, you should say that, this is an indication. But Maxwell law, it's a law. Maxwell say that, and you have to, I just give you the so-called justification, okay?
Yeah, I respect the law, but I'm just asking that are there any cases that they are not the same, so they are always the same, or
They are always the same, yeah. Because Maxwell, okay. Because actually Maxwell equation actually can be derived from Lorentz information. Okay, and the point is, okay, as a actually this by making, okay, we just finished. Okay, I'll make this comment later. Okay, in any case, okay. So what do we have? Okay. Okay, let's try that again. Again and again and again. Okay, I just want to. Okay, we have a divergent E equal to. Okay, a curve B mu 0 J, right? I mu 0 J. Okay. E equal to 0 and curl E equal to. Okay, that's the Maxwell equation up to, when Maxwell combine all the phenomena, all the law, real Sava law, whatever law, you contain these four formulas. And okay, he just made it because in the mathematics, okay, when you specify the divergence and curl, divergence and curl, okay, Helmholtz law, Helmholtz law, Helmholtz field, say that you specify anything. So Maxwell just specify all this one, okay, except he found out this one is inconsistent. Okay, and so he just made this, he just add this up to make it, self-consistent. And so he just present that one, and according to Sommerfeld, you as a student, at that time, with the electric field, you have this Biot-Savart law, you have this Lenz's law, you have whatever law, it's all very confused. But after that, it all becomes so clear. So if you read the book by Sommerfeld, you always, again, he just started, as I told you, start by Maxwell equation. Okay. So what is JD? JD is equal to partial D, partial T. Okay. Okay. And D is equal to epsilon E. Okay. Okay. And you can have, okay. If you add up, then divergent curve B is 0 and mu 0. Okay. Divergent J is 0 only in the static case. But if you have in the time changing field, you have a JD. JD is divergent D, divergent E. So that means divergent E partial T, and that's wrong. So that becomes divergent J plus partial rho partial T equal to 0, which is actually a conventional charge. So in this way, it's the equation becomes self-consistent. Okay, let's make it. Yes. Okay.